Okay, so let's look at section 3.2, which is conditional probability. This is where it gets a little trickier. So let's say we have a bag of marbles here. We have 2 blue marbles and 3 red marbles. And we're going to actually grab a couple of marbles. So first we're going to reach in, we're going to pull out a marble, and we are not going to put it back. So at first, let's say we pick the 1 marble and we get a blue marble. Okay, well, we had a 2 out of 5 chance of getting that blue marble, right? Because we had 2 blue marbles over 5 total marbles. But I don't put it back in. So now my bag looks different. Now my bag has 1 blue marble and 3 red marbles. So now the probability changes. The probability of getting a blue marble here before I grabbed one was 2 over 5. But now the probability of grabbing a blue marble, is going to be 1 out of 4 because I have 1 blue marble out of 4 marbles. The probability of grabbing a red is going to be 3 over 4 because I have 3 red marbles over 4 total. Okay, same idea. If the first marble I grabbed was a red marble, well, I had a probability of 3 over 5, 3/5, of grabbing that red marble because I had 3 red marbles out of 5, but I didn't put it back. So now I have 2 blue marbles and 2 red marbles. I'm going to pull a marble again, but it's now dependent on this bag of marbles, not the first when I bag of marbles. If I'd thrown it back in, then the probabilities would stay the same. But because I did not put the marble back in, I did not replace it, that changes the probabilities. All right, so we need a little notation here. This is called conditional probability because the probability is based on what happened when I pulled the first marble and did not put it back in. So the conditional probability is the probability of an event occurring given that, another event has already occurred. That's that straight line. So when we write the probability of B given that A happened. So in this case, let's look at this bottom one. We're going to say for this bag here, we want to know the probability of picking a red given that the first pick was a blue. So the first pick was a blue. And now that I've picked that blue and I don't put it back, now I want to know the probability of picking a red. Well, I have 3 reds, 3 red marbles out of 4, and so the probability would be 3 over 4. Right? It would be different if I had picked a red first. Then I would be up in this other bag and picking a red, given that I picked a red for the first time, I now have 2 reds out of 4 total. Okay, so you can see the probabilities are going to change, and it depends on what happened when we pulled that first marble. Okay, so let's look at this. We've got 2 cards are selected in sequence from a standard deck of 52 playing cards. Okay, our standard deck. Find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced. So we are not putting the first card that we picked back into the deck. Okay, so the issue is we pulled that king, right? We pulled it out of the deck and we put it in our pocket and we didn't put it back. So the problem is I now only have 51 cards. I don't have 52 cards anymore because I pulled that king and put it in my pocket. But I still do have 4 queens left because I didn't take any queens. I only took a king. And so the probability is 4 over 51. If they ask for a decimal, pop that in your calculator. Sometimes they give us a table. So this is a table that shows the results of a survey in which 2,276 social media users were asked whether they have ever been offended by something they saw on social media. Find the probability that a user is male given that the user was offended by something on social media. Okay, so we want the probability that the user is a male given that they were offended. Okay, so I know that I'm only going to use the data for someone who's been offended. So that would be this column right here. I don't care about any of the rest of the columns. I only care about the people who were offended. Okay, so this is really important. You have to start with the given that and then work backwards. So I know that I'm going to use this column of people who were offended. Therefore, I know that the total on the bottom is going to be 1,151. And I want to know the males out of, so 1,151 are all the people that were offended, and I want my numerator to be the males. So that would be the 532. Put that in my calculator, and I see that the probability that the user is a male, given that the user was offended, is 0.462. Here it is written up again, right from the book, if you want to look without all the writing on it. All right, let's try another one. We have find the probability that the user is female given that the user was not offended by something on social media. So this is the same idea, but we're using different data. So we want the probability that the user is a female given that they were not offended. Okay, so we're going to take this column of not being offended. Right? That's the second column here. My total is 1,125. That's the denominator. The number of females that were not offended is 549. I'm going to divide those, get a decimal, and therefore the probability that the user is female, given that they're not offended, is 0.488. So we have lots of formulas in probability. We are not going to go real far into probability, just a couple sections here. But what happens is you want to look and see if two events are independent or dependent on one another. So if they're independent, we don't really care about the given that. I'm going to show you some examples in a few minutes. But if they're dependent, then we have to be careful. So dependent would be like picking the card and not putting it back in. Well, now we have less cards, and so the probability is going to change. So the probability is determined based on us already taking a card. Okay, so let's look at some examples for independent and dependent. Makes more sense. So the first one is selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from that same deck. All right, so what happens is when we pick a king, there are 4 kings out of 52 cards. So the probability would be 4 out of 52. But now they say not replacing that card. So we take that king, we put it in our pocket, we don't replace it. So the problem is when we pick that second card, now we only have 51 cards to choose from because that other card's in my pocket. I still have 4 queens, so I still have 4 out of the 51 cards that I have left. So these are dependent, right? The picking the queen is dependent on that king that we did not put back in. Okay, the second one is tossing a coin and getting ahead, and then rolling a 6-sided die and obtaining a 6. Okay, well, those have nothing to do with each other. Tossing a coin and then rolling a die, they have nothing to do with each other, and so we consider those independent. All right, then we have driving over 85 miles per hour and then getting in a car accident. That's probably dependent. I don't know. Here in Texas, people drive that fast all the time, but we're going to go with that would be dependent. So these formulas are on your resource sheet. I'm going to show you how to get through the problems without really looking at the formulas per se. When we have the probability of something and something, we're going to use multiplication. So I know probability is a little strange, but and is going to mean that we're going to multiply. Okay, and we're just going to have to be really careful that if the two events are dependent upon one another, we are going to have to watch and see how that changes the probability. And so that's this first one. If they're dependent, then we're going to have the probability of A times the probability of B given that A happened. Okay, so that's like with the cards, picking a king, not putting the card back, and then picking a queen. We had to change the denominator because we didn't put the card back. Whereas if they are independent of each other, then we can literally just multiply the two probabilities together. That would be the tossing a coin and then rolling a die. They don't have anything to do with each other. Their probabilities don't affect each other, and therefore we could just straight multiply them together. I know we keep using this same example, but let's say we're picking two cards. So we're picking a king and then a queen, but we do not replace the king. Okay, so picking the king, we have 4 out of 52 is our probability of picking the king, but then we put it in our pocket. We don't let it be part of the deck anymore. And so now when we go to pick the second card, the denominator is only 51 because we have one less card, but I still have all 4 queens. Okay. And so 4 over 51 is the probability of picking the queen given that the king is in my pocket. Right now, if I multiply those, put them in my calculator, multiply them, I get 0.006. All right, then we have a coin is tossed and a die is rolled. So these are independent of each other. Find the probability of tossing a head. Well, there's only one way to get a head out of two sides of a fair coin, so that would be 1/2. Remember, this is and, so we're going to use multiplication. And then the probability of rolling a 6, there's only 1 6 on a 6-sided die. So there's one side out of 6 sides. And so that would be 1 over 6. We're going to multiply those together. If they ask for a decimal, pop that in your calculator. Okay, again, this is just all of that worked out without any writing on it. That comes right from the book if you want to take a look at it that way. Okay, so the probability that a salmon swims successfully through a dam is 0.85. Find the probability that 2 salmon swim successfully through the dam. So they haven't given us any other information to think that these are dependent upon each other, like one salmon gets in the other one's way or something. So I'm going to assume these are independent. So I want the probability of 1 salmon successfully swimming through the dam and a second successfully swimming through the dam. So since it's and, I'm going to multiply. So I'm going to take 0.85 times 0.85. That gives me 0.723. All right, the second one is 2 cards are selected from a standard deck of 52 playing cards without replacement. Find the probability that they are both hearts. Okay, so remember hearts is, we've got 13 cards that are hearts, right? So the probability that we're going to do the probability that we pick a heart in the first card, then we put that one in our pocket, we don't put it back in, and now we're going to pick a second heart, given that I put that first one in my pocket. So for the first heart, I have 13 hearts out of 52 cards. That works. This is an and because I'm picking the first heart and a second heart, so I'm going to multiply. Now the second one, I have to change both the numerator and the denominator. So I did not put the card back into the deck. It's still in my pocket. So I only have 51 cards left, but I also only have 12 hearts left because I put 1 heart in my pocket. So now I have 12 out of 51. So I have 12 hearts left because one's in my pocket. I have 51 cards left because one's in my pocket. And now I put that in my calculator and multiply those, I get 0.058. All right, let's try another one. So we have ACL reconstructive surgery. The probability that the surgery is successful is 0.95. So we want to find the probability that 3 ACL surgeries are successful. Okay, well, we know 1 is 0.95. So we want 1 and 2 and 3 to all be successful. So we are going to come down here and multiply 0.95 times itself, the 3 times. When we do that, we get 0.857. So these are all 3 successes. Okay, now on the second one, they say that they want them to be, or that none of them are successful. So we're going to use what we know about complements. We're going to take 1 minus the successful, which is 0.95, and that gives me 0.05 would be that it is not successful. And I want all 3 to be not successful. So I'm going to go ahead and multiply 0.05 times itself 3 times. And look how tiny that is. It gives me 0.000125. All right. Finally, it says find the probability that at least 1 is successful. So here's the problem with this one. If we tried to add up all the combinations, we would have to do, let's go up here. We'd have to do all 3 successful. We'd have to do successful, successful, fail, successful, fail, success. We'd have to go on and on, right? We would have to add all of these up, and it would be crazy. We don't want to do all that. So what we're going to do instead is, instead of adding all those up and having to multiply and add, we're going to use what we know about complements. It says at least 1 is successful. Well, that means if we take 1 minus the probability that none of them were successful, we would know the probability of having at least 1 be successful. So that's what I did. I took 1 minus the all 3 being unsuccessful, and I get 0.999. Okay, so again, these are worked out without all the writing on there and with some different wording if you want to take a look at it that way. Okay, so let's look at a few examples that are like the homework. So this one says, list an example of 2 events that are independent. Okay, so not putting money in a parking meter and getting a parking ticket. That's dependent because if they come by and see your car and you have no money in the meter, you're going to get a ticket. Rolling a die twice. Okay, so if you roll a die, you get an answer. If you pick it up and roll it again, it has nothing to do with the first roll. So those are independent. A father having hazel eyes and a daughter having hazel eyes, that's dependent. Selecting a queen from the standard deck and not replacing it. Not replacing it is what makes it dependent. And then selecting a queen from the deck. So if we replace it, they would be independent. But since we did not replace it, it's going to be dependent. Okay, so we have this table. We have 250 male and 250 female workers. They're all ages 25 to 64, and they were asked if they contribute to a retirement savings plan at work. Okay, so we've got the males in the first row, females in the second row, and then the total. Here we have whether they contribute or they do not contribute. Okay, so for the first one, they said, find the probability that a randomly selected worker contributes to a retirement savings plan at work, given that the worker is male. Okay, so remember with these tables, you have to start with the given that. So given that the worker is male means that I only want to use this row. That's it. Okay, I'm not going to use any of the data other than that. So given that the worker is male, I'm going to only use that first row. My total is 250, so that is going to be my denominator here. And I want to know the probability that they contributed given that they're a male. So contribute is 116 over 250, the total, and that gives me 0.464. Okay, so you have to be very careful. Don't write on your monitor, but kind of just look at which row or which column you need. Okay, the next one, I'm going to circle down here. The next one is the probability that a randomly selected worker is female, given that the worker contributes to the retirement savings plan. So remember, you have to start with the given that. So the given that the worker contributes tells me that I only want this column. I don't care about the rest of the data. I only care about that first column. That means that my total on the bottom is going to be 248. And I want to know the female. So I'm going to grab the 132 over 248 here and put that in my calculator, and I get 0.532. All right, I know we've done this one a bunch, but we're going to do it one more time. So we're going to pick 2 cards from a standard deck of 52 cards. We are not going to replace the card. So we want to know the probability of selecting a 10 and then selecting a 9. So there are 4 10s. So there's 4 cards that have a 10 on the face, and then that's out of 52. So picking a 10 would be 4 out of 52. We're going to put that card in our pocket. So since we put that card in our pocket, we now only have 51 cards left, but we still have all 4 9s, right? We didn't pick a 9. So we still have all 4 9s. So we're going to go ahead and put those in our calculator, multiply them, and get the decimal to 4 decimal places. Okay, so let's see what we have here. It says in a recent year, about 37% of all infants born in a country were conceived through in vitro fertilization, so IVF. Of the IVF deliveries, about 28% resulted in multiple births. Okay, so notice how it says of the IVF deliveries, about 28%. Okay, so what happens here is they said find the probability that a randomly selected infant was conceived through IVF and was part of a multiple birth. Okay, so the probability of in vitro or IVF would be 0.37. Then the probability that we get a multiple birth given that we have IVF, right? That's the second sentence, is 0.28. And because we have the word and, we're going to multiply these two together. So that's going to change in the next section. But when you see the word and, you're going to multiply. That part's not going to change. We're going to have a different word. So 0.37 times 0.28 gives me 0.1036. Okay, so that's for the first one. B says, find the probability that a randomly selected infant was conceived through IVF, but was not part of a multiple birth. Okay, so I know this is worded really crazy, which is why I'm showing it to you. If there's not part of a multiple birth, I'm going to take 1 minus the 0.28 because 28% were multiple births. The rest are not. So 1 minus 0.28 would give me 0.72. All right, and then finally they say, would it be unusual for a randomly selected infant to have been conceived through IVF and to have been part of a multiple birth? So we found that probability up here. That is the 0.1036. Well, for this to be unusual, it has to be less than 0.05. Okay, so less than 5%. So we're sitting here at a little over 10%. Well, that is not less than 5%, right? It has to be very tiny and almost 0 for a probability to be unusual. So we're going to say that this one is not unusual.